function, it's the sum of two things. It's the integral of the derivative of the inside plus the integral along the boundary of the derivative of the boundary changes times the inside of the formula. Okay, so that gives us this formula here. Now, if we drop all of the arguments from this, that becomes C pi prime times S prime times CS, right? That's this first term here. And then we bring all this stuff to the other side, and we get negative S times CS prime plus pi prime, right? Now, the deadweight loss, right, is CS of 0 minus CS of P minus pi of P, right? That's the definition of deadweight loss. What's the total potential social value? There's no profits when the price is 0. Minus the total social value created at the price. So the derivative of deadweight loss is the same as negative CS prime plus pi prime, right? And so we can just call this whole term here deadweight loss prime, right? So then how do we rewrite this expression? Monica? How can we rewrite this expression?
Where you drop the arguments?
Yeah, because we now have this new definition, deadweight loss prime is equal to
Right, so
CS.
then it's just the pi prime S prime CS would equal the deadweight loss prime.
That's right, except that you also have to multiply by S.
Right, yeah.
Right. And, yeah, there we go. Right? Okay, so now, Alexandra, can you turn this into an elasticity?
So elasticity is the same as like S prime over S.
Yeah.
So you substitute that.
So you could divide by S there, right?
Yeah.
And then it's not quite just that, you also need to multiply right by whatever you're taking elasticity with respect to, right? Which here is pi. So you have to multiply and divide by pi.
Okay. So it's you want to do the S prime.
Yep.
Times that and then you divide by pi.
Yep.
So it's elasticity times specific plus over pi equals
Yep.
derivative loss over
Exactly. Yeah. So you S prime over S times pi is the elasticity of supply. And then to get that pi up there, you need to divide through by pi, and let's put that underneath the consumer surplus. And let's divide both sides by pi prime. This should be pi prime here, sorry, not CS prime. And we get elasticity of supply times CS over pi is equal to deadweight loss over pi prime. And this gives us this formula. So this is the key formula which captures the trade-off that we've been talking about throughout the class. Elasticity of innovation supply times the ratio of consumer surplus to profits, which is basically like the amount of the externality being created, right? The ratio of how much external benefit they get to how much they capture is equal to the marginal cost of providing incentives, because this is how much dead weight loss do we have to create in order to create a little bit of profits, right? And this means that we should give more protection to intellectual property. These are the marginal benefits, these are the marginal costs. If Osama, is Osama here? No. Does anyone else want to interpret the comparative statics of this? Yeah, Matt.
If the marginal benefits are higher, the marginal costs are lower. So basically the numerators on the left side are higher and on the right side are lower.
Yeah, so let's go through each one of those. Can you give me sort of intuitively, if I increase this one, what does that correspond to?
If you increase elasticity. So like if you give more supply, you'll have a higher like level of innovation.
Yeah, so what this is saying is that if the innovators respond more to material incentives, if you get a greater increase in innovation when you increase the rewards to innovation, then you should have more intellectual property protection, right? So you guys actually probably saw something quite similar to this on the problems that you just turned in. The more elastic things are, the more important it is to reward them, sort of, right? So the more elastic their innovation supply is to the rewards given, the more intellectual property protection you want. The more consumer surplus there is for every unit of profits, the more reward you want to give. And the more deadweight loss you create on the margin per unit of profit, the less rewards you want to give, right? And so we'd now like to sort of verify the most basic intuitions that this leads to, and what, Kenneth, would be sort of the basic intuitions that this would suggest to us about the level, how the level of reward should differ depending on situations?
Well, we need to take into account the elasticity to determine how much the weight loss is going to be with respect to innovation. I mean,
Yeah, that's right. Yeah, so basically we should suspect that when innovation supply is more elastic, we're going to have more protection, right? And on the other hand, when there's a lot of dead weight loss for every unit of profit, there should be less protection, right? So like if the numbers that showed up in that Heidi Williams thing were really big, you wouldn't want too much protection for intellectual property. If the difference between the different countries that I showed you on that other picture were really big, you'd want a lot of intellectual property protection. And this formula is just saying exactly what you need to measure to quantify that stuff, right? Okay. And we can take a broader interpretation of these things. In particular, Heidi Williams' thing was about the various different types of dead weight loss, not just from like the product market, but also from follow-on innovation. And entry into the market of drug was not exactly the same as CS over pi, but anyways, these things were very related. Yeah, David.
Yeah, maybe I'm just a little confused, but
Yep.
where does the reward for innovation factor into that equation? Is that represented through pi prime or?
Yeah. So the thing is, these are like implicitly determined. So remember that as we give higher rewards, right, the derivative of dead weight loss is going to get larger, and the derivative of pi is going to get smaller. And so as the reward gets greater, this will get greater. So if this gets larger, then we're going to have to go to a point where the ratio of these things is larger. So I'll show you a graph of that. I'm going to show you how I get it, but you see the right-hand side is going to sort of look like this, and the left-hand side is going to look like this. So anything that shifts up the left-hand side is going to shift up the optimal degree of protection. But let me show you how we actually get a graph like that. Okay, so we want some way to set up a demand form that allows us to change how much dead weight loss we have to get for every unit of profit, right? And remember that pass-through affected the ratio of consumer surplus to profits. It also turns out that it affects the ratio of dead weight loss to profits. I don't know if I showed you guys that, but you can just see if a demand curve is very convex, then there's going to be a big area of dead weight loss. So higher pass-through, the more dead weight loss we get for every unit of profit, and a simple class of functions that allow us to vary that are the constant pass-through demand functions. And in fact, some of the special cases of this are all the demand curves we've been working with in the class so far. So constant elasticity, which we've been working with a bunch, is a special case of constant pass-through. Linear is a special case, exponential, and also that concave demand curve that I showed you guys was also a special case. And its general form is given by this. You don't really need to know this. This is just something you can plug into Mathematica. But this form is really easy to work with because the formula for consumer surplus is, again, just really simple. The formula for dead weight loss is very simple, and so forth. So with this in hand, we just need some sense of what the relevant elasticity might be and what the right pass-through might be. So there's a bunch of different studies on elasticities. None of them are very convincing, but I think roughly we think the elasticity is somewhere between 0.5 and 1. The way that these studies usually work is that you look at some time where the potential market for some product increased in size, and then you looked at how that created more innovations. So one example of that would be as people in a society age, are the types of drugs that are being created more targeted to elderly people? That'll tell you how innovation supply is responding to changes in market size. Another example would be on the iPhone App Store. When Apple announced that they were going to make it available to Verizon, suddenly the number of people who were going to get iPhones and buy apps got much bigger. And you can look at how much that increased profits on apps. And you can also look at how many more apps were created than were expected based on the historical experience. And you can use that to sort of measure the elasticity of innovation supply with respect to the incentives to create them. Pass-through is quite a bit harder to measure. That Einov et al. 2011 paper that we looked at in the monopoly lecture showed that it could be very, very large potentially. There's a paper by Basenko et al. Which found that it's usually between 0.5 and 2. And so I'm going to run with that assumption from now on. I'm going to assume the pass-through is somewhere between 0.5 and 2. Okay, so we can just draw out these graphs using these formulas from Mathematica, right? All we need to know is deadweight loss prime, which we get just by taking the derivative of this. We need to know pi prime, which we get by taking the derivative of p times q. And we need to know the ratio of cs to pi. And then we just get these graphs. So in the base case, which is this blue curve and this red curve here, and this blue curve and yellow curve here, I've assumed that pass-through is 0.5, and the elasticity is also 0.5. And then I'm going to see what happens if we increase pass-through or we increase the elasticity. So we should think that when we raise elasticity, right, that should lead to a larger amount of patent protection. What I've graphed here is the amount of protection, the fraction of the monopoly price charge against the left and right-hand sides. And if we increase the elasticity over here, we see that that increases the amount of protection from 0.5 to about 0.65. On the other hand, if we start with a pass-through here and we raise the pass-through rate, which increases the amount of deadweight loss for every amount of profits, then the amount of protection falls from about 0.55 to about 0.45 here. Okay. And that's exactly the results that we wanted to get, right? And this indicates that in the case where we want to have the lowest amount of protection, it's about 0.45. In the case where we want the highest amount of protection, given the parameters we talked about, it's about 0.65. Yeah, Matt?
How do you measure protection in a quantifiable number like that?
Aha, that's the next step. So how does that line up with the practice in the real world? So one way we could do is we could think about the length of patent protection, right? Imagine that a product is going to, earn the same amount of profits each year for the rest of eternity, right? And then if we have about a 5% interest rate, a 20 years of patent protection is about 1 minus 0.95 to the 20 of the effective life of the patent, right? You get about 64% of the total life of the patent in terms of profits from a 20-year. So that's pretty darn close to the numbers that we were thinking about, right? Now, probably you earn more profits in the early years, so this is probably something a bit more like 80%. But, patent protection is pretty incomplete. You don't get a full monopoly. People can usually compete with you a little bit along the edges. So this is pretty darn close to the range that we're thinking of.